experiences in a career of chemical engineering. He is the Director of Graduate Studies and Professor of Chemical Engineering at the University of South Carolina in Columbia. Please join me in giving a warm USC welcome to Dr. Andreas Hayden.
All right, let's get this thing started here. So I kind of prepared a few slides of who I am and how I got to where I am right now. Try to put a little bit in there of what I'm actually doing, and hopefully I can kind of make some connection with some of you, and can excite you to some degree that chemistry and chemical engineering are currently great areas. We really messed up this world. There's a lot of work for us to do to clean it up, okay? So if you think of global warming, if you think of all kinds of problems, global problems that they are, that need to be solved, chemical engineers and chemists are the ones who have to solve them, okay? So I feel like the next 50 years are actually really great, because it's not that if you have some old plant, keep on cranking out some old chemical or something like this. You really have to change things. And that means people who are creative, you get opportunities to really do something, and not just, follow other people's lead and just keep on chugging along. So I'm a big believer that the next 50 years are gonna be awesome for us. Lots of fun. All right, so who am I? So I'm actually a German American now, actually. So, but originally I'm from Germany, kind of from a village north of Hamburg, which is kind of one of the big port cities in Germany. Kind of typical chemical engineering background. Dad was a mechanical engineer, mom a hairdresser, kind of middle class background. Work ethics was always very important for us. Parents were able to provide kind of a stable upper middle class childhood, very protected in many ways. My sister was actually the first who went to college in my family, so I was the second, because my sister's 4 years older than me. Like a lot of engineers, I always kind of liked math. And like a lot of people who you probably saw in this environment, they probably told you that they had one or two teachers during their time that really impacted them, right? It might have happened right now that you have one or two teachers that kind of have a real impact on you. So I certainly had this, kind of a weird thing for probably most Americans. I had the same math teacher from 5th grade to 13th grade. In Germany, we used to go to school for 13 grades, well, we still do actually, instead of 12. And I had the same guy who taught me math every year, semester by semester. And this was Dr. Braun. Kind of unusual, because he was actually a physicist from the accelerator that is in Hamburg. So he had a PhD in physics, did research for many years, and then decided that he wanted to stop doing research and actually teach some kids. And he started becoming a teacher when I was one of the first students he ever had. And anyhow, he was an outstanding teacher for me. Actually, he was not very popular with most of my peers because he was brutally hard. His expectations were the ones from a scientist and not teaching 5th graders, essentially. For me, he was just perfect because he didn't go the easy route. He really cared about teaching the difficult things. And I hope that you have also one of these teachers who you kind of impacts you. And of course, this was very extreme because I had him for so many years, right? Again, I cannot be more thankful of him. I actually had, I was lucky, I had a great chemistry teacher, Mr. Mühlbach. So he was kind of actually liked by most students. So in that sense, he was kind of very different to Dr. Braun. But I had him for 5 years in chemistry in Germany, and I pretty much did all of organic chemistry in high school. And we had 5 days a week chemistry, 3 days a week we did experiments. and 2 days the pure theory essentially. And kind of in that environment, I was kind of really wanting to then go into chemistry or chemical engineering. Given that my dad was a mechanical engineer, it was pretty clear I had to do some form of engineering, right? You have to do something real, right? You build something, create something in this world. But engineering is a great job. It's not necessarily perhaps for a kid whose dad is a senator or something like this. Okay, sure, if you're in that circle, become a lawyer, become a doctor or whatever, that's fine. But if you really want to kind of move up the food chain and have a stable, good job, which is not a bullshit job, but you do something that's actually of value, and where you can go home day in, day out and say, I actually did something of value, then an engineering job is a great job. And for me, this bullshit job is very important because you see more and more people who have these bullshit jobs because that's the only thing that's out there. And you know, it's so much easier to rip someone else off to make your money than to actually do something of value. Okay? And people have to figure out for themselves what they want to do, but I do believe most people want to feel good about their job, and that's more important than having perhaps a little bit more money, as long as you feel good of what you're doing and have enough money. And as an engineer, you will always have enough money. All right, so before I went to college, I actually, so this is very cool in Germany, and if you want to become an engineer, they take everyone. High school diploma, you're in. Of course, they kick most of you out afterwards, but there are so many engineering jobs out there that there are never enough students, okay? Of course, also college is free in Germany. That was nice too. But even before I could actually go there, I had to do military service. In Germany at the time, we still had a conscript system. Military was good for me, and I think it's good for a lot of people because you see other people. You don't just see the people from your neighborhood that you grew up with, but very different type of people. I remember when I joined, shared my room with one guy. He was 3 times my size, tattoos all over, and I just thought, that's not me. But you know what? I got along just fine. Just fine. And having these different experiences and exposing yourself to something completely different is good for you. You just learn from that. Okay? Scary sometimes, but you just learn from that. So anyhow, the other thing, of course, I learned from that is the importance of cars for a lot of people, certainly in Germany. But man, whenever the duty was over during my military time, everyone just ran to their cars to tune them up for the next car race or some shit like that. But anyhow, that's what it was, and that's what we did for a year. So then I went to college, studied chemical engineering just because it was this love for math and chemistry essentially. And then I had this lucky fortune that I could study abroad. Again, my whole family, all just from northern Germany, never really left northern Germany. And that's good and fine, but I had this opportunity to just, go for a year, study a year at UC Berkeley, San Francisco, California. Who can't say no to that, right? Just for a year, all paid, man. So, of course, I took this. Of course, I met my wife there, who's from Los Angeles, and that's why I am here, right? So, because Americans don't want to leave the country. So, and in that sense, I was, of course, willing to see the beauty of a completely new place. And academically, my time at UC Berkeley was also great because obviously that's a world-class research university. And you see different things in such an environment, in a very competitive environment, than you see at my school in northern Germany or let's say here, right? Again, because it's so competitive. And at the same time, it was it's great because you're exposed to so many things, and I can only encourage everyone, get exposed to different things, right? I know a lot of things cost money, and that's why we don't do certain things, and it's effort, but we need to put in some effort if you want to grow, right? And I know all of you guys are still young, you want to grow, right? Mentally grow and become the best of yourself. So anyhow, at the whole time I was always sure that I would want to end up in industry, and never considered that I could ever become a professor. That was kind of out of the realm of a possibility, quite frankly, because working class people do not become professors, right? They might become great engineers and have fun doing that, but that was kind of my thought process. So I always thought the two big chemical companies, BASF, Bayer, that's where I probably would end up, hoped to end up working for, and try to have my impact there, which would have been just great. As a chemical engineer, though, particularly if you want to work for some of the big chemical companies, you kind of need a PhD. So I said, okay, let's need a PhD. Let's do a PhD. Can't be that complicated. But then, of course, so I kind of worked in computational catalysis, co-advised actually between the University in Hamburg and UC Berkeley, working on this N2O decomposition over iron Zenison-5 catalyst, and that just sounds all complicated. So let me say a few words about catalysis. So you have all taken chemistry classes, right? You have all, to some degree, heard the term catalysis. So catalysis is a process of altering the rate of a chemical reaction by adding a substance known as a catalyst, which is not consumed and can continue to act repeatedly. So the key thing is, it's actually important. So catalysis accounts for over 95% of all products and over 80% of value added in the chemical industry. So overall, 20% of the world's economy depends directly or indirectly on catalysis. Estimated economic impact is on the order of $12 trillion. So it's again, often small amounts that we add to something, but they have a huge impact on what's going on. So now I have a few slides to, I don't know how successful I'm going to be, but give you an idea of what computation catalysis is. So I like to think of it as the in silico design of novel catalytic materials for converting hydrocarbon fuels into electricity, natural gas into liquid fuels, liquid organic hydrogen carriers, plastics recycling, biomass utilization, solar energy to fuels. I'm working on all the green stuff right now. In other words, the real question is, can the computer revolution of the last 60 years also accelerate the design of catalytic materials to revolutionize the chemical industry and decarbonize our economy? So that's essentially the hypothesis of computational catalysis. Again, when you think of what it really comes down to is, when you have chemicals, you have these complex, you have a lot of challenges when you want to make new materials or chemicals. And one of the key challenges is really the complexity, that you have many different species in there. If you want to not use petroleum anymore, but want to use biomass, then you create a pyrolysis oil, oftentimes out of your biomass, and then you have thousands of species in there. What really happens in catalysis and what kind of makes it kind of special, so you have often these supported nanoparticles, and the crazy part is each ball here is approximately 1 atom. Okay, so you have actually, they're tiny, they're on the order of a nanometer, and a lot of these atoms have different neighbors. That means they are chemically different. That means they do different things, or slightly different things at least. So you have a lot of complexity at the small scale, and you have environmental effects, you have these reaction networks, all these elementary reactions that you might learn in some of your organic chemistry classes. of what could all happen. And you try to look at all of this on a computer. Right? Solve the Schrödinger equation, or an approximation of the Schrödinger equation, and try to predict how everything happens with time. So not just thermodynamics, kind of what happens in equilibrium or something like this, but what happens with time if I add a certain component to the system. So again, one of the key things really is when it comes to chemistry, chemical engineering, or computational catalysis is you look at a lot of things that happens here in the atomistic range, but we really want to produce something at the plant scale, right? At the macro scale, when it's about yards, when it's about buildings that are feet tall where the reactor is in. And what a lot of challenges are, how can we use this information at this atomistic scale, transfer to the reactor scale, and how does this reactor scale information change what happens on the atomistic scale? So that's kind of in a nutshell what computational catalysis is. And again, we try to then design catalysts that do the things. So you know, one approach what we do here, we build these models of atoms essentially. This could be our, you know, a platinum cluster on some support here. And then we study all these elementary reactions. You know, machine learning can help find some of those reaction pathways, how things actually move along. We use, I don't know if you have seen this equation here already, iron equation, to get the rate constants. And then we really get directly macroscopic observables, right? What really can be measured in the reactor, what directly affects what you get out of our products. So anyhow, so during my PhD, I was interested in this N2O decomposition. N2O is actually the third most important greenhouse gas after CO2 and methane. 31% is of the anthropogenic N2O is of industrial origin. That means that you have localized sources. You know, processing localized amounts is much easier than sucking the CO2 out of air and doing something from this, because the concentration is so low, right? But adipic acid plants and nitric acid plants are the main culprits for the anthropogenic N2O. And N2O, if you look at it, it's not too, you know, if you can just split it and produce N2 and O2, you have something completely harmless, right? Just air. So anyhow, the truth is, when I started this project, I was not at all interested in any green chemistry. Okay, I wanted to make something of value, and there was a time where, or it still is, we are flush with natural gas, methane, shale gas revolution, some of you might have heard. And we wanted to make better use of the methane than just burning it. And actually using N2O as your oxidant, you might be able to make methanol out of that. So that was all the rage, and that was what I tried to do. But I failed, okay, like everyone else failed. So now I still want to write a PhD, so you have to make sure, let's respin all my work in something useful, okay? And I was able to respin it, that sure, that all the work we did is also very important for this specific purpose. And that's how I ran with it. And again, this is kind of what we did. We looked at this iron that is in 5, so that's, think of sand that has a very specific crystal structure, and you put some, in this case, just small amounts of iron in there in the right locations, and then you can essentially split this N2O up at low temperatures and produce a harmless gas out of it. And you know, this was one of the, I felt one of my big breakthrough during that time is where I put in the effort to look up all the literature that was out there and plotted all the literature from all these different people on a graph, and I noticed they all get something different. I knew that kind of, but I did not know that all their results more or less fall on a straight line. And with computational catalysis, I was able to explain why they all fall on a straight line and why they might be different. And it was just that in their reactor, they have small amounts of different amounts of water in their system. And we are talking parts per billion, parts per million amounts of water in the gas streams, essentially. So anyhow, after my PhD, I was in this dilemma that I wanted to go to industry, but I don't have a green card to go to industry in the US. But my future wife, or now wife, and at that time girlfriend, they didn't want to leave the US. So I decided, okay, so I have to do another postdoc in the US because, you can easily come to the US to do a postdoc, even without green card. And I studied some multi-scale models for nanoparticle applications. Reality, that impact, the research wasn't as impactful. I mainly just showed that a lot of things that we are all working on in this specific area was kind of useless and we should stop working on that and stuff. So I spent 1.5 years doing that. And, but during that time, I really noticed that I really love science and research, and that as a scientist, you have one of these rare opportunities that you're not just working for someone else, but you're also very often working for yourself. Because all the honor, all the things that you do is always just your name. Yeah, there's a university name or whatever also, but people remember your name, nothing else. So that's one of the great things of science, is that you really often work primarily for yourself. Yes, it's my research group in Columbia, South Carolina that does something. We do all these things. Yes, of course, all the money goes through the USC system and so on, but everyone just identifies you or yourself with this. And this is, of course, very nice. So at that point, I decided that perhaps I should give it a shot and try to become a professor. I really love science, and as a professor, you have the opportunity to work in science your whole life long. And you are allowed to work on the problems that you want to work on. And nobody else determines something else. Of course, you need to pay money for it, no question about it. So nothing is free, but anyhow, that's how I ended up in Columbia, South Carolina, because they made me the offer, and I couldn't reject. And I was able to move my wife from Los Angeles to Columbia, South Carolina, which is not that easy, let me tell you that. So, but yeah. So now I built their research group again in computational catalysis. We work a lot on shale gas utilization, biomass chemicals, plastics, upcycling, again, liquid organic hydrogen carriers. And now I try to do more also in CO2 capture, storage, and utilization. You see, a lot of these areas are kind of trying to do something good for this world. There are global challenges. And I'm not saying that we will solve all these challenges, but we will work on them. And we will educate the people who will be the next ones who work on them. And that feels actually very gratifying. Okay, in no way is that a bullshit job. So anyhow, my especially in my group is these so-called solid-liquid interfaces and how to use machine learning and uncertainty quantification and catalysis. These are all just details, okay? Just that it shows you that, yes, obviously the computer revolution, AI and all these things are important, and they go into science and into research and whatever you do, okay? So, so that's of course nice too, right? Because everyone knows AI these days, right? And you can use that not just to select the next TV show you want to watch, but also perhaps do something good with it. Sounds pretty good to me. So, so yeah, I have two more slides to perhaps give you another idea. A PhD never stops because, again, one of my projects is still methane utilization, which of course didn't really work as well during my PhD, but now we want to do it even harder. We want to use oxygen from air and not N2O. Anyhow, so just to give you an idea here of methane, so we again have a lot of shale oils and gas in this country. The problem with the shale oils is they come with a lot of gas. A remote location, what do you do with the gas? And then you see, if you go to North Dakota, flare sites, Texas, flare sites, you just see burning at night. It's all burning flames, right? because they don't know what to do with the methane. Methane is a bad greenhouse gas. You can't just release it to the air. So what do? You just burn it. CO2 is better than methane in the air. So, but of course it's a huge wasted resource, right? If you can make something useful, if you can make the problem is you can't transport a gas easily, right? So there are no pipelines from these remote locations that you can just have a gas pipeline and pipe it away this way. But if you can make a liquid out of it, right? Liquid, then great. Somewhere is a rail station somewhere, and you just dump it into those containers and bring it to marketplace, right? So that's again often the idea. If you want to do what you want to do with methane, again you want to often use it because it's small scale locations. So you want to do it at relatively low temperature. Partial oxidation is one solution. So and I have here one motivating slide to perhaps show you what a computational catalysis scientist tries to do. So what's the idea? So we want to convert methane partial oxidation to methanol because methanol is a liquid, right? So how do I design a catalyst that can do that? So we said, okay, we want to have these single metal sites that must strongly interact with CH3 and methane. Well, nothing interacts strongly with methane because it's such a symmetrical molecule. You've all built it, I'm sure, in one of your chemistry classes, right? You cannot attack it in any shape or form. So you need something that's really out there, really can attack it, grab it, do something with a strong interaction. You need so-called surface stabilized mechanism. If you have it, the real problem is your product, methanol, has a weaker CH bond than the methane. So if I can't break my methane, I for sure can't break my product. And you know what happens when I break my product? I produce CO2. I burn it. So that's exactly what I want to avoid. I don't want to flare it anymore. I want to make something useful out of it, right? So we wanted to say, okay, we need these single atom sites. Now, you still have this problem that how do I make sure that I can activate methane better than my product? Let's say I can activate it, but now again, usually 99.9%, then will the product be reoxidized to burn? So we thought, what's the difference between the carbon atom in methane versus the carbon atom in methanol? Well, the carbon atom in methanol sits next to an oxygen atom. So it's probably slightly positive charge on my carbon atom in methanol. Well, in methane, there is charge neutral or slightly charged negative heat, right? So perhaps I can make use, if I make sure that my metal site is electropositive, has a slight positive charge, right? Then it will repel the carbon from the methanol, while it doesn't do that for the methane. And in this case, you might be able to impart selectivity in this process. And of course, then you also need to activate oxygen, right? When you have reactions with two gas molecules, there's a lot of entropy in a gas molecule versus when it's on the surface. So you need to bind both molecules as strong as possible. It's impossible to really bind methane strongly because it doesn't interact with anything. But again, you need to at least do the oxygen. So again, our idea was to use rhodium-doped graphene that we put on nickel support that kind of satisfy some of these requirements. But again, that's kind of the thought process. How do I do something like this? Okay, and actually the catalyst that we designed now, they tested it, and it does do the chemistry. Unfortunately, still at a too high temperature to be really economical right now. But the idea, this is just one way of thinking. You know, how do I solve such a problem? I don't just randomly throw stuff together, right? So anyhow, so what's the key message? If you love science and math, want a stable career and be part of the solution to global challenges, then chemistry and chemical engineering offer great career pathways. Just be courageous. There's little to lose, much to gain. So of course we do have summer internship opportunities. I'm not the one who organizes them, but the guy whose office is directly next to mine. So if you have, email me, I can transfer information directly to him. and there are plenty of opportunities out there. Yeah, that's pretty much it here. I'm open, of course, to questions.
Quick question. So